All right, I thought I'd just make a little answer key for this week's quiz since I won't see you before the big test. And let's take a look at number one. It's a graph, and it's a transverse periodic wave on a string. It's stretched along the x-axis. The figure above shows the y position of a point on the string as a function of time. What further information, if any, is needed to determine the wavelength? All right, so what this graph is telling me is the period. Right, it's a graph of position versus time. When time is on the x-axis, they're telling me the position. The period and the amplitude. So the amplitude is no help for finding the wavelength. If we have the period, then we also have the frequency because they're the inverse of each other. So to get the wavelength, we just need to know the speed because speed is equal to wavelength times frequency. And so velocity is another word for speed. Amplitude is no help, but the amplitude is actually on there. The frequency is on there already, and that's why the answer is A. Sure, let's save it. Whatever. A student shakes a horizontally stretched cord, creating waves. The graph above shows the vertical position as a function of time. It's the same graph. The student then tightens the cord so that waves on it travel faster. Right, so we've changed the medium so that the waves can travel faster because the speed of a wave depends on the medium. And if you increase the tension in the medium, it will travel faster. Shake the cord to make the graph look the same as above. So we want basically so the speed is faster. And basically the speed is equal to wavelength over period. So if we increase this, right, we have to decrease this. And if we decrease the period, that means we increase the frequency. So shaking it faster is increasing the frequency. That's more shakes per second is an increase in frequency. A student is observing an object of unknown mass that is oscillating horizontally at the end of an ideal spring. The student measures the object's period of oscillation with the stopwatch. The student wishes to determine the spring constant of the spring using the measurements of the period of oscillation. Which of the following pieces of equipment would provide another measured quantity that is sufficient for the spring constant? Well, let's just not write everything down. Let's just remember that the period is proportional to mass over the spring constant. So we have this, check, and we want this, check. So what do we need? We need mass. Which of these things will measure mass? Well, balance. Using a number of measurements, the student determines the following spring constant, mass of object. So the total energy, so basically the energy is oscillating back and forth between spring energy and kinetic energy. And let's switch over to text box. So the kinetic energy is equal to 1/2 times 0.5 times 3.9 squared. Oops. And I guess the font is just a little crazy. Let's make it more smaller. Come on, font. That's more better. And the potential energy due to the spring, U spring, is equal to, equal to 1/2 K. K is equal to 85. X squared, X is 0.3. In any case, you can do both of those calculations and they both come up with 3.8. And that didn't help. Here, why don't we do this for fun? 3.8. Oh, well, I thought that was going to be funner. Alan and Beverly are on opposite sides of a large room, and Alan says something to Beverly, and Beverly doesn't hear him. So Alan repeats it louder, and now she hears it. What happened? So basically, loudness is responsible for disturbing the air molecules in your life, and oh boy. So that's the one. They are greater displacement. The greater displacement, more energy, more loudness. All right, number 6, the speed at 0.65, which is right here, is about right here. 0.65 is right here. And probably the drawing tool would be better for that. 0.65 is right here. So how do you find the speed of something on a slopey graph like this? It's the slope of the tangent line is basically what it's the instantaneous speed at that time is equal to the slope of a tangent line. So you draw a straight line right here and measure the slope of that line, and that's the speed at that point. The total distance traveled by the object from 0.35 to 0.4. So here we are, we're at 0.35 right here, and then we're at 0.4 right here. So we got to just pick the best answer, and I notice that from here to here is 4 centimeters. And so it definitely doesn't go 4 centimeters, and it doesn't go 0 centimeters because, right, it did do something. So basically we have to choose between 2 and 6. Well, 6 is ridiculous. It can't be more than 4, so it has to be 2. The frequency is basically this graph is telling us the period, so we just find the period. So the period is the difference between this time and this time. So it's 0.7 minus 0.2, which is 0.5. So the period is 0.5, which is not what they were asking me. They were asking me for the frequency, which is the inverse of the period. The inverse of a half is 2, and there it is. Whoops, there it is. Hey, last page, finally. All right, so we have these waves coming together. They're going to pass through each other. So this basically is asking you, do you understand that waves pass through each other? And so this one's got a height of 2 here, and this one's got a height of 3 here. And so as they come toward each other, when they're at position B, they're going to constructively interfere. And at point B, we're going to see 5. So whenever X, so these are the only, so these answers are gone. Because at point X, we have to add together to make 5. So basically the question then is, do you understand, if you think they bounce off of each other, then you're going to pick the wrong answer. And if you understand that they pass through each other, you're going to get the right answer. Because after they pass through each other, the big one, 3, is going to be at position A, which is Y, 0.3. So B was the answer. And then the other one, the little 2 one, will be over here at position C, which is Z, 0.2. A tuning fork. So, we did this lab, and basically what we learned was that columns of air will resonate at specific places depending on the pitch of the tuning fork. And so when you're pulling that tube out, definitely the shortest air column will give you the first resonance. And then so the length of that, so if you hit this point right here, that's the first one. And then if the pipe were long enough, you could go this distance again, and that's where the next one would be. And so that's the other answer that's correct. And thus endeth the lesson.